Hello everyone, so we are in chapter 7, analytic trigonometry. Coming to this chapter, we already know about the 6 trig functions, and the way we approached the trig functions, that is the sine, cosine, tan, cotan, secant, and cosecant, was to represent them or define them as coordinates of a point on a unit circle. So that was our approach to defining those trig functions. We did not use the right triangle ratios in the right triangle to do so. And then we looked at the graphs, the basic graphs of these trig functions, where we allowed for transformations in the form of shifts to the right, left, which we call the phase shift, and for some scaling, that is adjusting the period of these trig functions. The one thing that we got out of that, among other things, was that all trig functions, all 6 of them, are periodic. That means they repeat themselves after each rotation or revolution around the circle. So the natural thing to do now is that having defined the function as a mapping from x to y, we would like to be able to establish the return path and create a two-way communication between the function and between the domain and the range values. And that's where we are now. In chapter 7, we're going to be covering 7 sections, so it's a rather long chapter, but it's one of the most important aspects of trigonometry, what we do in this chapter. In particular, solving trig equations is a key skill that we would like to really learn and go forward with. So let's begin with section 7.1, the inverse sine, cosine, and tangent function. Now, as I mentioned, let's say, for instance, if you look at the sine function, we define the sine function to be as the y component of a point on a unit circle. So here you go. I don't mean it to go like that, but you know what it does. There you go. Now, in order to try to find the inverse of the function, if you recall, we mentioned functions that are one-to-one, only one-to-one, have inverse functions. Well, in the case of all of our trig functions, none of them are one-to-one. So for instance, if I draw a horizontal line here, you can see that it will cross the graph of sine. This is the graph of sine x. It will graph it at definitely more than one point, which makes the function not one-to-one. But we would like to be able to make it to where we can actually do this. So one way to accomplish this is to restrict our domain. So for instance, in the case of sine, and how we restrict the domain, by the way, isn't unique. There is a convention, common convention, so everybody kind of works along the same way, same path. But if you want to restrict the domain here, then one way to do it, for example, I can look at this segment right in here. If I look at that segment, the function is one-to-one. If I look at another segment, maybe look at from here to here, the function is one-to-one. So there are different ways we could restrict the domain. Now, how the domain is restricted in general, by convention again, so everybody pretty much has agreed to this, is that if you look at the domain of the sine from negative pi over 2 to pi over 2, and if you just look at this segment, then the function is one-to-one. And as a result, we don't need the remaining segments, right? So I can literally remove these other parts. And there you go. So we don't need that. And this is how we make this function one-to-one. So in the case of sine, that's how it's done. Now, the other thing I want to mention here is the following. If we think in terms of a functional relationship between x and y, I'm going to use this function machine to try to clarify what it is exactly that we accomplish with the inverse trig functions. So now in an ordinary situation, let's say this is the measure of angle theta. This is like the domain. Instead of x, I'm using theta for the angle. And I'm dropping in an angle in radian. And the machine here, let's say this is the sine machine. Okay, so it will process the theta. In this case, it will do sine of pi over 6. And let's say we know that sine of pi over 6, that's what it'll do. It will evaluate sine pi over 6, and it will output a 1/2, a value that is between -1 and 1, right? Now, this is just the function. Now, what about the inverse? Well, the inverse, remember, establishes the return. I'm just going to go like this. F inverse for now, or we can use the inverse notation. There you go. Because we've already talked about inverse functions in algebra. So we know the notation. All right, now the idea of inverse is this. See, notice this time now you plug in a 1/2, the output from f. We plug it in here, and then let's say I have now, using the inverse notation, sine inverse. Okay, and then this would be sine inverse of y, wouldn't it? Because that's what's going in. So we're going to feed 1/2 into this machine. And then the output from this clearly should be pi over 6, right? It will give you theta equal pi over 6. So what I'm doing here is I'm trying to show you this. When we process the inverse trig functions, inverse sine, inverse cosine, whatever we're going to do in a few minutes, the output or the outcome or output of every trig function is the measure of an angle. Okay? So for instance, again, if the problem says find the inverse sine of 1/2, then this will be the measure of an angle. And of course, more specifically, the answer is going to be pi over 6. So you see how that works? That's very important to note, because sometimes we just get lost in the shuffle here. Like, what is it that I'm doing with the inverse function? What is this telling me? So remember, we're trying to find a measure of the angle from the function, from the output of the function. All right. Now, so this is how we're going to restrict the domain. The restricted sign, by the way, sometimes they write them like this. In some textbooks, they actually use capital Sine X to show that this is a restricted domain sign. And what do we mean by that? This is exactly the same as Sine X, except this is good from negative pi over 2 to pi over 2. I know some older trig textbooks used to do that. The newer textbooks do not do this. So for restricted domain cosine, that's what this is, cosine x. And we will see in the case of cosine, for example, if I look at the graph of cosine, again, this is not a one-to-one function. You can see it will fail the horizontal line test. So in order to create a one-to-one function for cosine, they have agreed to restrict their attention to simply from 0 to pi. Over that domain, restricted domain, the function is 1-to-1. Okay, and this is for cosine x. So I'm going to write it as 0 to pi. Now, I'm not going to stay with this notation that I'm doing right now, capital S, capital C, and then capital T for tangent and so on. I just wanted to point that out, that these are, if you think of them as subset of the general trig functions of their own type. So cosine x, restricted cosine, sine x here is the restricted sine. All right, so going back to, let's say sine x, there you go. Therefore, now that we have indicated what the restricted sine is, we can find the inverse, right, by definition of inverse. So if I have y is equal sine x, remember to find the inverse, we did this in the algebra portion of the course, is when we swap the x and the y. So we get x is equal to sine y. And this is the inverse function, right? By simply swapping, we create the inverse. Now we would like to be able to solve for y if we can, so we have an explicit form. And the way to do this is by simply redefining it. So this is what we mean. X equals sine y means y is equal to arc sine of x. Okay, now I did mention arc sine x. This is also another way to write the inverse function. A lot of textbooks choose to do this also, write arc sine from time to time. And the reason is because that superscript -1, notice I called it superscript, not exponent -1. This could be confusing to people because remember we have negative exponent, so like a to -1 is 1 over a. Well, when we say arc sine of x, that doesn't mean 1 over sine x. So it's kind of a sloppy notation, but it is what it is. And again, it's, almost every science textbook is done this way. But the arc sine also is correct. The arc here references an angle. And it's just a reminder that this inverse function is the measure of the angle. So that's what this arc sine means, angle of sine. And it goes back again when we talked about the unit circle. If you recall, we defined this to be the arc sine is portion of the circle. This is the arc of a circle. And then we defined the central angle theta. And the length of the arc was t, right? We said theta is equal to t for a unit circle, a circle of radius 1. Okay. And there you go. For a circle of radius 1. So anyway, I'm just trying to motivate why they call it arc. That means the measure of the angle, because arc and the angle are the same with respect to the unit circle. Alrighty. Now, so based on this, keep in mind how we're going to restrict the domains, and then we're going to define these inverse trig functions. So now I'm going to bring up better graphs of these for you, and then we'll proceed with the inverse of tangent next. Okay, and there they are. So the one you're looking at on the top left, this is the one for sine. This is sine x. Remember, that's the restricted sign because our domain is from -pi/2 to pi/2. And of course, the range of sine is -1 to 1. Now, once we restrict it, then the inverse trig function, this would be the arc sine of x directly below it. And remember the relationship between range and domain of a function and its inverse. The domain of the function becomes the range of the inverse, and the range of the function and domain of the inverse are the same. Okay, so we simply swap those. And then the graph is going to look like so. In a moment, again, I'll display where we can graph these using the knowledge of, or the fact that the graph of a function and its inverse are symmetric with respect to this line, right? So we'll do that in just a few minutes, but this is kind of how the graph of the inverse is going to be. Okay. Now, for cosine, the one in the middle, the top is cosine x, restricted domain cosine. Our domain is now restricted. Let's see. This is actually, sorry, I got these backwards. Let me move these up. This is the cosine function, and this is the inverse. Didn't mean to misplace them. And there you have it. So the one on top is the graph of cos x. And of course, the domain of restricted cosine, we're going to go from 0 to pi. Okay. That's how we can make the function 1 to 1. So that's what that is. And then the inverse. The one below is the inverse. So this is the arc cosine, if you will. And this is again what the graph would look like. For tangent, the restriction occurs between -pi/2 and pi/2. See right in here? Not including, because those are the asymptotes. So that means for the inverse, therefore, the range is going to be negative pi over 2 to pi over 2, and domain is going to be the same as the range of the function. So the one that you're looking at here below, that's arctangent of x. Okay, now the graphs again for arctangent looks like this. And notice, by the way, the domain of arctangent is negative infinity to infinity. Okay, whereas that's not the case. That's not the case for sine and cosine. All right. And then going to calculus and higher, we tend to work with inverse trig functions of sine, cosine, and tangent by far more than we do for cotangent, secant, cosecant. They're out there. We will cover them in the next section. But we tend to stay with these more so than others. Okay. And then I'll show you in a moment how I kind of remember how to work with these, because it is important to note the domain and range of these when we solve equations, and then later on in your calculus courses when you do integration. That's important to know what the domain and range of the inverses are. Now, finally, I just want to reinforce the fact that the graph of a function and its inverse are symmetric with respect to the line y equal x. All right, so if you look at this one, here's again the portion we're looking at sine x, right? Remember, the graph of sine looks like that, correct? That's between negative pi over 2 and pi over 2. And the graph of its inverse by reflection is going to look like this. Okay. And here's how we have sine again, restricted between negative pi over 2 and pi over 2. For cosine, remember we restricted cosine between 0 and pi. So that's what this portion of it is, right? And then we can reflect this with respect to line y equal x, and we get the graph of its inverse. Tangent, if you recall, tangent looked like so. This was the graph of tangent, right? And reflection about the line y equal x will give us the graph of the inverse tangent. Again, I just want to emphasize the importance of the symmetry between the function and its inverse. And of course, we always have f inverse of x equal x for all functions, right? For any function that's 1 to 1, this relationship holds. The other one was f inverse of f of x equal x. Now these, by the way, these relationships hold only in the case here of f of that composition f inverse of x is within the range of f or within the domain of the inverse. This relationship holds if we are in the range of the outside function, or it will be the same as domain of the inside function, right? Remember, range of f inverse is the same as domain of f, and vice versa. So these relationships only hold for those under these conditions. Okay, so we pretty much have this done. Now for and the one way I'm trying to think about a way to help you be able to do this without having to memorize all of these bits and pieces of it. Okay, because again, these are important, and we will do this for cotangent, cosecant, secant later too. So how are we going to remember all these domains and ranges? This might help, and I'll extend this as we go through the remaining trig functions. I will extend this as well to those other three. But for sine, if I think about the unit circle, again, this is a tool that helps me remember the range of inverse, which means domain of the restricted domain of the function. So for sine, this is think of this as my unit circle. Okay. So for the arc sine of x, not sine, this is for arc sine. The range of the inverse is from negative pi over 2 to pi over 2. And remember, range of inverse is the same as domain of the function. So I tend to just at least visually remember this. It's easier for me to visual things, to be visual, and try to imagine things than to memorize expressions. So for sine, this is kind of an image that I have in mind. Now, what does this image look like for cosine? Again, this time I have again a half circle that stretches from 0 to pi. This is the range of cosine inverse x. Okay, from 0 to pi. For tangent, the range of the inverse, not the domain, because domain is all real numbers. Actually, let me do this. Redraw what you had for sine. That's redrawing the unit circle. Okay, and the only thing is the endpoints are not included. So the range of arctan or tan inverse is almost the same as the range of the arcsine or inverse sine, with the exception the endpoints are not included because, again, tangent of pi over 2 and negative pi over 2 are undefined. Those are the asymptotes of the graph of the function. And there we have it. Okay, so hopefully the way that I'm doing this, and I will continue as I work through these future sections, you'll see me. I'll be drawing these half circles often, and this is how I will remember them rather than remembering things like this. Okay. All right, so let's take a look at some examples and see how we can put this to use now. All right, in our examples, let's suppose we want to find the exact values. Okay, so in my first example, let's say I want to find the exact value of the angle theta, which is the arcsine of root 2 over 2. Okay, so by definition of the inverse, that means sine theta is equal to root 2 over 2. Okay, and then at this point, if you remember when we work trig functions such as sine theta is, here's one thing I also want you to do. Label your axes instead of x and y as cosine and sine. This is negative cosine, this is negative sine. Okay, that really will help us going forward. And remember, this is justified by definition of trig functions as coordinates of points on a unit circle. So for a unit circle, this is going to be what? X, and this is going to be y. Now, sine is root 2 over 2. It's a positive quantity, correct? Well, sine could be positive in the first quadrant, and it could be positive in the second quadrant. The question, well, which of these do I choose in order to find the inverse? And remember, for the inverse, we restricted the domain. For sine, we only allow from negative pi over 2 to pi over 2, correct? So that's why I said I will be redrawing these circles many times. And there you go, or half circles. Now, because the range of sine inverse only allows from negative pi over 2 to pi over 2, in other words, the measure of the angle has to be in Q1 or Q4, right? Therefore, we rule out the possibility of the angle being in the second quadrant. And now here's the measure of angle theta. Now, root 2 over 2 is one of our special values, right? Something that will go nicely alongside of this chapter. For every time I'm trying to evaluate, either solve a trig equation or evaluate a trig expression involving inverse or the functions themselves. because we use the special values often, so it's worth redrawing these triangles over and over. The way we label this is the side opposite 30, half the hypotenuse. So if this is 1, that's 2, this would be 3, square root of. And we also have the 45, 45, 90 triangle, correct? And for that one, the sides are 1, the hypotenuse is root 2. So these half circles that I have, okay, these along with these triangles are going to help us tackle just about every problem that involves finding exact values of either the function or the angle, which is the inverse trig function, or solving equations. So we're going to stay in with that theme throughout the chapter. Okay, therefore we recognize root 2 over 2 as a special value for an angle that's 45 degrees. Remember, root 2 over 2 is rationalized version of 1 over root 2, correct? That's how we got root 2 over 2. So the unrationalized version is 1 over root 2, and because we're doing sine, 1 over root 2, so the measure of angle has to be 45 degrees, or in radians, pi over 4. And there we have that one. Okay. And let's do another example. With these inverse trig functions, the more we do, of course, the more comfortable we feel about working with these inverse trig functions. So let's do now negative root 3 over 2. Again, we're going to cycle through these values for those special angles. Our special angles are 30, 45, 60, and of course we have the quadrantal angles, right? 0, 90, 180, 270, and 360. Okay, to do this one again, by definition of inverse, what does this mean? Well, this means cosine of the angle theta must be negative root 3 over 2. Now, for cosine, I recall this half circle. The fact that cosine is negative, because we know cosine is positive in the first quadrant, it's negative, right? In the first quadrant, cosine is positive. In the second quadrant, cosine is negative. Well, this is a negative value. So the measure of the angle must be in the second quadrant. True? And here's what I know so far. And we have root 3 over 2, so this is what it looks like. That's the measure of angle theta. Now we have square root of 3 over, probably too not steep enough. There you go, that's a little better. So that's the measure of angle theta in the second quadrant. And square root of, if this is negative root 3, this is 2, because remember, cosine, we define cosine as the ratio of x to r. Okay, and this is for circles that are not necessarily unit circle. If it's a unit circle, then cosine theta is just x. But if it's not a unit circle, then it's not. All right, and just put 1 here so you know that this one is a unit circle. Okay, and this would be 1. Okay. Okay. So there we have it. And maybe this is again, that's more realistic. This is negative root 3. And this is 2, this is 1. Now it's more realistic because the altitude here, the side of this triangle is going to be 1. Square root of 3 is about 1.7. Okay, anyways. Now we have the measure of the angles. This would be the point P corresponding to a point on a circle of radius 2 now. All right, and going off of our triangle, therefore the measure of the angle has to be 150 degrees. 150 degrees, that's 5 times 30. So that's 5 pi over 6. And there we have the value of this trig of theta. Let's take a look at another example. In this example, suppose we want to do arctangent of negative root 3 over 3. And again, the unrationalized version of root 3 over 3 is 1 over root 3. So this triangle is the one we're working with. And because for tangent, we're looking at y over x. Okay, so y is 1. This is y, and x is 3. And therefore, the measure of the angle has to be 30 degrees. Okay, let's see how this is going to work out. We do have a negative value. So that means, by definition of inverse, tan theta, or arctan of theta, is negative root 3 over 3. Which, again, I want to write as negative 1 over root 3. They're the same thing. Now, this time, we're going to look at the range of tangent, which is right in here. Well, tangent could, the inverse tan, the measure of the angle is either in the first or fourth quadrant, just like sine was. True? Now, so if I do this, and the fact that it's negative, we know in the first quadrant tan is positive, in the fourth quadrant tan is negative. Correct? We know that from the earlier work with the trig functions. So therefore, the angle is this angle right in here, and it's going to be a negative angle, because remember, the range of tangent is negative pi over 2 to pi over 2. So the angle has to go in this direction. That means you have negative theta. So it's going to be a negative angle. The answer will be negative. Now, 1 over root 3, well, if I draw a better drawing of what's going on in that segment, we get this. Let's see. I'm going to have, and remember, this is the measure of the angle theta. It's negative 1 over root 3. So the hypotenuse is 2, and there you have it. That means the measure of this angle is going to be 30 degrees negative, right? Because it's going in a clockwise direction. So the answer is negative pi over 6. That'll be the answer to this example. Okay, so just a few examples for each of those: sine, cosine, and arctangent. Let's take a look at a few more examples, different kinds. Now this time, suppose I'm going to look at the composition now of f inverse of f of x. So I'm going to do cosine inverse of cosine of 4 pi over 5. Now, I can't just quickly jump to the conclusion that it's 4 pi over 5, just because if the inverse, you have a composition of the inverse and the function, this is the answer. Well, that's not always true for trig functions. The reason, because we have that restricted domain, or think of it as restricted range for these inverse trig functions. So I'm going to actually draw this thing out. And I'm going to find the angle 4 pi over 5. Well, 5 pi over 5 is pi. So this is, let's say, 4 pi over 5. True? And remember my circle. Again, this circle is really what's saving me personally as far as remembering how to process inverse trig functions. Okay. Now, I'm clearly within the domain, right? Or I'm sorry, the range of the inverse. And this is cosine inverse x. So clearly, I have a value that's within the range of the inverse. So the answer is going to be 4 pi over 5. No problem. Well, let's do another one. Suppose I want to do arctan of tangent of negative 3 pi over 8. So let me draw this one. For tangent, remember we go from negative pi over 2 to pi over 2, right? That's the range of the inverse. And this is tan inverse we're working with. Okay, and the value is negative 3 pi over 8, whatever that is. There you go. That's negative 3 pi over 8. All right. And we are well within the range of the inverse, so that's negative 3 pi over 8. Again, we have to be within the range of the outside, which means domain of the inside function. And in both cases here, we're good. Now, what if, also, since we've done cosine tan, let's do a combination of sine of the arc sine of, let's say, 1/4. Let's see what this will be. Now, this time, we have arc sine of 1/4, so that's the measure of the angle, right? Okay, so by definition of inverse, sine theta should be 1/4. All right, sine theta is 1/4, and it is positive. Arc sine is positive. And this is my half circle for arc sine theta now, or x, arc sine x. And we have 1/4, which is a positive value, right? The measure of the angle is 1/4 radian. There you go. The measure of the angle. This angle is 1/4. Again, it's worth saying that it's 1/4, and the measure is in radians. There, radians. All right, and so we're good. We are in the range of the inverse. Or I'm sorry, in this case, we are within the domain of the inverse. Remember, range of the outside, domain of the inside. So that 1/4 is within the domain of the inverse function. As a result, the answer is 1/4. All right, because as long as we are within negative 1.57 and 1.57 on the y-axis, that's the range. Domain is from 0, in this case, domain is from 0 to 1. Okay. And we are good with that one. Now let's take a look at another one. Let's do something that we have to make an adjustment for. Suppose I'm going to do arc sine of sine 9 pi over 8 now. Okay, so question is, will that composition be 9 pi over 8? So if I look at, again, the range of arc sine, the range of inverse, this is only allowed to be from negative pi over 2 to pi over 2, correct? The measure of the angle is 9 pi over 8. This is 0, that's pi. 9 pi over 8, well, 8 pi over 8 is pi. 9 pi over 8 will be an angle here, wouldn't it? So this is the measure of angle theta, which is clearly not, it is not where it's supposed to be, right? It's supposed to be in here, but it's outside of the circle. So what do? Well, in that case, we need to find an angle that has the same trig measure. Okay, and it has to be within the range of the inverse. Now, in the third quadrant, sine is less than 0, right? And being a little sloppy here, well, sine without an argument is sin, right? So there you go. Sine theta has to be negative because we're in the third quadrant. Well, how can I get negative for the inverse? That means I cannot go in the first quadrant because there sine is positive. So I need to go to fourth quadrant to get an equivalent value for sine. All right. Therefore, the measure of the angle is going to be negative pi over 8. So notice how we have to reflect this back inside of the this region. Okay, the highlighted region. And that's what we did. All right, so what does that mean? That means the value of this, the composition of a function, inverse and a function, in this case is going to be negative pi over 8. Remember, the outcome of every arc sine or every arc cosine, every inverse trig function is a measure of an angle. And there is that one. Let's do arc tan of tangent of 4 pi over 5. Again, the question, will this be 4 pi over 5? Well, let's do our circle. The half circle for tangent. The range of arctan is, I said tan, sorry, arctan. The range of arctan is from negative pi over 2 to pi over 2. Now, 4 pi over 4, well, 5 pi over 4 would have been pi, right? 4 pi over 4 pi over 5 is going to be in here. True? So here's the measure of the angle, theta. This is 4 pi over 5. Well, and in the second quadrant, tan is negative because cosine is negative, sine is positive, right? So in here, tan theta is negative. Well, so if I reflect this over here, I cannot because tan is positive there. So this is ruled out. That means I have to now reflect it. And the reason is because, because I need to be within the range of the inverse. That's why I emphasize the importance of that. So there you have it. We need to be inside of that region. The angle needs to be there. Therefore, I'm going to simply reflect it across, and the measure of the angle will be negative because it has to be between negative 90 and 90. So this angle is going to be negative pi over 5. You simply subtract pi from 4 pi over 5, and you get negative pi over 5, and that will be the answer. Okay, and let's do one more of this kind. And I want to do let me see, let's do another one where we actually have to solve for x. So hopefully this will help you get the idea. In this next example, this will be our last couple of more, and that'll be it. So for this one, suppose I have 4 arc sine of x equal pi. So actually, it's like solving an inverse trig function equation. Now for this, I'm going to divide by 4. So arc sine of x is equal to pi over 4. And remember, this is theta, correct? Therefore, by definition of inverse, that means, what does that mean? Well, that means sine of pi over 4 is equal to x, right? By definition of inverse. Again, we have sine of pi over 4 equal to x, and sine of pi over 4 is root 2 over 2. So x is going to be root 2 over 2. Okay, and that's within the range of inverse again, pi over 4. Remember the range of sine. This time is positive. It's in the first quadrant, right? It's pi over 4. There. Okay. Now let's do one last example here. The next example, suppose I have 3 arc cosine of 2x is equal to 2 pi. So divide both sides by 3, and we get arc cosine of 2x is equal to 2 pi over 3. True? And then here again, by definition of inverse, that means cosine of 2 pi over 3 is equal to 2x. And cosine of 2 pi over 3, well, 2 pi over 3 is 120 degrees. There. That's the measure of angle. Right, that's 2 pi over 3. So if I build my triangle here, this would be 2 pi over 3 is 120, so this angle is going to be 60 degrees. This is 30 degrees, and my triangle will look like this. I have 1, 2, square root of 3. 1 will be negative because cosine is negative in the second quadrant. Remember, x is cosine. All right, and so cosine of 2 pi over 3 is going to be negative 1/2. Negative 1/2 is equal to 2x. Divide both sides by 2, and x is negative 1/4. And there you have it. We're able to solve these inverse trig equations. All right, and that is all we have for this lecture. So again, please review these. Try to do these half circles I'm doing and follow how I'm using them, because this will really help you, especially when you go to your calculus series. It's hard to memorize range and domains. For me, it's much easier to, let's say, memorize these half circles. And we got 3 more of those in the next lecture, next section, for cotangent, tangent, and secant. So we're going to restrict those as well and proceed. We're done with this lecture. Thank you all for watching, and hopefully I have you in another lecture, another video.